Question 10, Part B. Two particles A and B start moving on the x-axis at time t equals 0. The position of particle A at time t is given by x equals -6 plus 2t minus half t squared, and the position of particle B at time t is given by x equals 4 times sine t. Part 1. Find expressions for the velocities of the two particles. To find the velocity of particle A, we differentiate the displacement equation of particle A. And the displacement equation is x equals -6 plus 2t minus half t squared. So to find the velocity, we find dx dt, so differentiating x with respect to t, we get 2 minus t. Now to find the velocity of particle B, we differentiate its displacement equation. So the displacement equation of particle B is x equals 4 times sine t. Differentiating x with respect to t, we get v equals dx dt, which equals 4 times cos t. Part 2. Use Part A to show that there are exactly two occasions, t1 and t2, when these two particles have the same velocity. Using the graphs drawn in Part A, the graphs represent the velocities of particles A and B. Now recall from Part 1, we found the velocity of particle A, which is v equals 2 minus t. The velocity of particle B was v equals 4 cos t. Now if we sketched v equals 2 minus t and v equals 4 cos t on the same set of axes, we would obtain exactly the same graph that we sketched in Part A. Now the graphs that we sketched in Part A, the x-axis, well, is the x-coordinate, the y-axis of course is the y-coordinate, but if we represent velocity versus time, the y-coordinate becomes velocity and the x-coordinate becomes time. But we would obtain exactly the same two graphs, and the points of intersection represent the points where the velocities of both particles are the same. And I've labeled them here. So there's one here and one here. We discount this point of intersection because we're only interested in values of time greater than or equal to 0. In other words, quadrants 1 and 4. So going back to our explanation, the points of intersection of the graphs represent the times where the velocities are the same for time t greater than or equal to 0. And by inspection of the graphs, the value of t1 is between 0 and 2, and the value of t2 is between 2 and 6. Part 3. Show that the distance travelled by particle A between these two occasions is 4 minus 2 times open bracket t1 plus t2 close bracket plus half times open bracket t1 squared plus t2 squared close bracket. For values of time between t1 and 2, where t1 is less than 2, the particle is moving to the right. Hence, the distance travelled is given by x of 2 minus x of t1. We'll call this expression number 1. Now, after time t equals 2, that is, values of time between 2 and t2, the particle moves to the left. So at time t equals 2, the particle changes direction. Hence, the distance travelled is given by x of 2 minus x of t2, and we call this expression number 2. Now, it's important to note that at time t equals 2, the particle changes direction, and this needs to be taken into account when finding the total distance travelled. So to find the total distance travelled, we add both of these expressions together. So expression number 1 and expression number 2. Now we have two of these x of 2's, and so we get 2 times x of 2, and we can factorise out the negative from minus x of t1 and minus x of t2. So the total distance travelled is given by 2 times x of 2 minus open bracket x of t1 plus x of t2 close bracket. Now recall the displacement equation for particle A, which was x equals -6 plus 2t minus half t squared. So substituting t equals 2, t equals t1 and t equals t2 in the relevant spots, we get 2 times open bracket -6 plus 2 times 2 minus half times 2 squared close bracket, so that's 2 times x of 2, minus, now open square bracket, open bracket, minus 6 plus 2 times t1 minus half times t1 squared, close bracket, plus, open bracket, minus 6 plus 2 times t2 minus half times t2 squared, close bracket, close square bracket. So we can simplify the numerical component. 2 times x of 2 is negative 8. And we have negative 6 minus 6, which gives us negative 12. So that's inside the square brackets here and here. And we have plus 2 times t1 plus t2 in brackets, so factorising out the 2, minus half times t1 squared plus t2 squared, so factorising out negative half. Now expanding the square brackets, we have negative 8 minus negative 12, so negative 8 plus 12, we get positive 4. Now we have a minus here and a plus here, so we get minus 2 times t1 plus t2 in brackets. Now we have a minus here and a minus here, so we get plus half times t1 squared plus t2 squared in brackets as required. Part 4. Show that the two particles never meet. The displacement curve for particle A, x equals negative 6 plus 2t minus half t squared, is a concave down parabola with the vertex at t equals 2. If you recall, at t equals 2, that's when particle A changes direction. Now at t equals 2, the displacement is negative 4. Hence, the displacement range of particle A is x less than or equal to negative 4, with x equaling negative 4 occurring only once at time t equals 2. Now, the displacement curve for particle B, x equals 4 times sine t, has a displacement range of x greater than or equal to negative 4 and less than or equal to 4. So the only time where particle A and particle B could meet would only occur at time t equals 2, no other time. Now at time t equals 2, the displacement of particle B is given by x of 2, which equals 4 times sine 2, which equals 3.637 and so on, which is not equal to negative 4. Therefore, the two particles never meet.